We are going to look at oxides, of which some are acidic and some are basic. And we're going to start out with acidic oxides. And here we go. Find the pH when 1.0 moles of SO3 dissolves in enough water to make 1.0 liters of solution. So this is going back to our reactions from chapter 4, and some of the more complex ones at the end were maybe some of the less common ones we don't deal with as much. But we got SO3 and combines with H2O to form H2SO4. So this is typical that a non-metal oxide will combine with water to form an acid. So non-metal oxide plus water forms an acid, and you can kind of think of SO3 emissions in acid range forming H2SO4 would be a pretty good example right here. All right, H2SO4 is a strong acid, but it's only strong for getting rid of the first proton. So that's where the Ka1 is large. Getting rid of the second proton, it's not a strong acid, but for a weak acid, it's on the stronger side of a weak acid for getting rid of that second proton. So let's look at this, and H2SO4 breaks up into H plus and HSO4 minus, and we'll look at it one step at a time. And we talk about it, if it's a strong acid, at least getting rid of that first H plus, it's essentially going to be 0 H2SO4, and my H plus concentration will be 1. Well, if it's 1 mole in 1 liter, and I take the negative log of it, that pH is 0.00. All right, will there be a contribution from the next H plus? Okay, yes, but it's going to be rather insignificant. We'll look, it's a weak acid, so now we're looking and saying 1.0 of this, and notice we already have 1.0 of this and 0 of this because we have the 1.0 H plus from before, and ultimately we're going to lose X. It's going to be really, really small compared to what it was before. And then what's going to happen is this is going to be 1.0. This is going to be about 1.0. And we can go ahead and do this. So we're going to do Ka2 equals H plus times SO4 minus 2 over HSO4 minus. And we plug things in with the Kas, and we get X, which equals SO4 minus is 1.2 times 10 to the negative second. Okay, notice this concentration of SO4 minus 2 is the same as the Ka. We learned that when we did polyprotics. Well, the H plus contribution is going to be that too. What if I add this to the contribution before and took like the negative log of 1.012? I get 0.005. So I guess I could round up and say maybe the pH would be negative 0.001, but it's virtually having no contribution right there. So it's really the H plus from the strong acid is what's determining the pH. The weak acid or the second H plus doesn't have much effect right there. Okay, let's look at a base oxide, which would be formed when a metal oxide combines with water, forming an hydroxide. So here we have 0.01 moles of K2O dissolves in water to make 1 liter solution. Take the K2O, H2O, and it forms 2 KOH. So this is one where you know this is a strong base. You just have to pay attention to your stoichiometry. If you have 0.10 moles of K2O, and you go through this 2-to-1 ratio of KOH to K2O, you ultimately get 0.2 moles or 0.20 moles of OH minus in 1 liter. And because it's a strong base, I can just say, hey, if OH minus equals that, I can say the POH is 0.70 and the pH would be 13.30. So notice again, it's a strong base and you're going to get a really, really high pH in this case. All right, that's metal oxides and base oxides, and then finding the pH of those. And that was page 14 of your homework packet.